Hi guys, today we are doing experiment N4, statistical errors of radiation. This is my group members. There are 9 content in our experiment, which is objective, equipment and material, introduction, procedure, table of data, task, discussion, conclusion, and lastly the reference. The purpose of the experiment is to demonstrate the statistical fluctuation in time of decay rate for a radioactive source of constant activity. This is a list of equipment and material used in our experiment. Radioactive decay is random, so its measurement of a radioactive sample is independent of the others. However, when many measurements are taken, the results show predictable patterns around an average count rate. This pattern helps determine how often certain deviation from the average occur. In this experiment, we will take 120 independent measurement and use simple statistical method to analyze the data, showing how to understand and manage the uncertainties in radiation counting. To calculate the average count for n independent, we use formula R bar equal to R1 plus R2 plus R3 divided by n, which is R is the number of count and n is the number of measurement. After that, to calculate the standard deviation, we use sigma equal to square root of R bar, which is R bar is the mean of the average count. Before we proceed to our experiment, we have to follow the procedure given. Firstly, configure the electronic as shown in figure 1. Adjust the voltage of Geiger-Müller tubes to its operating value. Set the 775 counter power supply to the minimum threshold. Refer to figure 2. Use the Thallium-204 source from the source kit and position it approximately 1 cm from the Geiger-Müller tubes window. Adjust the 719 timers as follows. Preset set to 1, multiplier set to 100, time base set to 0.01 minute. Press the start button on the timer and record the number of count registered. Perform 120 independent 1 minutes run without moving the radiation source. Record all count value R in table 1. Calculate the count rate R bar using equation 1. For each run, compute R minus R bar and record the value in table 1, including the sign.
I will continue our presentation with a data table. As the author can see on this slide, there are 120 count value data which is R that we took during the experiment. Let's move on to the next slide, which is for the task. In this experiment, there are 3 questions given. First, we need to calculate the standard deviation using the formula in the introduction part, and I have put the values in the data slide table. Next, the second question, we need to plot the frequency of rounded off events versus rounded off values. As the author can see in the next slide, this is a form of graph that we get by using Microsoft Excel. For the last question, does our plot follow a normal distribution similar to this figure? Yes, if I drew the graph using graph paper, we will get a bell shape. The source of error. First, in practical experiments, the counting time is finite. This limitation introduces statistical uncertainty as the observed counts may not perfectly represent the true average decay rate. Second, variations in the radioactive source activity, dead time in detectors, and coincidence losses. Third, when the radiation source is weak or the detector efficiency is low, the number of detected counts may be small. This can significantly increase the relative statistical uncertainty. Next, for the precaution step. First, extend the measurement duration to collect more counts, reducing statistical fluctuations and improving the accuracy of the decay rate estimate. Second, use detectors with low dead time and apply mathematical correction for miscounts, especially in high-activity experiments. Third, use a detector that is well suited to the type of radiation being measured, ensuring higher detection efficiency. For the last part is the conclusion. In conclusion, the system generating R values is generally consistent, with most runs aligning with the mean and standard deviation. However, occasional anomalies indicate errors needing further investigation to enhance stability and predictability.